Hello everyone, so welcome to the fourth lecture of week 4. So we were exploring various applications and architectures of recurrent neural networks. And in the last lecture we talked about how do you do sequence to sequence using RNNs. Now today we will touch upon a very interesting aspect of text generation, that is decoding strategy. That when you decode into a final generation, what are the various methods you can use. While I will cover this from perspective RNN, this is in general applicable to any architecture we will see later on, like transformers or any other model for decoding. So let us see what are the topics we are covering. So we are covering topics about decoding strategies, starting from greedy decoding, beam search decoding. We will talk about some sampling methods like random sampling with temperature, top key sampling and top P sampling. So before I talk about decoding, let's try a problem from the last lecture. So we talked about sequence to sequence RNNs, and we also introduced the concept of attention. So let's say you are using sequence to sequence RNN model with attention for machine translation from English to Hindi. That means English will go into encoder and Hindi will be decoded. Okay, and also assume that the vocabulary for English is 40K and that for Hindi is 50K. Now they have 300 dimension embeddings, both of these, and the hidden state of the encoder is 100 dimension and hidden state of the decoder is 200 dimension. Now the question is, what are the number of parameters that you need to train, and ignore the bias terms, right? So let us understand the parameters that we will need. In the encoder, I only have the connection from input to hidden. So encoder parameters. So input to hidden. So this will depend on the dimension, the embedding for the input, that is 300 dimension, times hidden vector, that is 100. Plus you have a hidden to hidden recurrent connection. So that depends on the hidden vector dimension, that is 100. So 100 cross 100. There is nothing else you have in the encoder side. Okay. Now let's see what happens in the decoder side. So decoder, you have again a connection from input to hidden, that is 300 times 200, because hidden dimension is 200 here, and you have hidden to hidden, that is 200 cross 200. Okay, and you also have a hidden to output, right, because you are now generating the tokens. So hidden to output. Now what will this depend on? This will depend on 200 into the size of your vocabulary, because you will decode, you will generate any token from your vocabulary, you will generate a vector of your vocabulary dimension, and vocabulary for Hindi is 50,000, so into 50K. Okay, so this would have been typically the parameters if you were using a normal sequence to sequence. So you can actually add all these, that are number of parameters, ignoring bias terms. Now what extra is added due to attention? Due to attention, what is happening? You are creating a dynamic context vector and you are feeding every time to your hidden state, right? So that means you have to have this connection. Context vector would go and give input to the decoder hidden vector. So how many dimensions you need? So first of all, what is the dimension for context vector? Now CI is nothing but a weighted average of all the encoder hidden state. That means it has the same dimension as the encoder hidden state. So that means dimension of CI are 100. Okay, and it is going to give input to hidden vector. So finally it has to be projected to hidden vector of the decoder dimension, that is 200. So that means I need to multiply it with a matrix, say W, you can say attention matrix, that will take this context vector and will add to other things, right? I mean, plus your u times h d I minus 1 plus w times x I, right. So, something like that will happen, and then you have a sigmoid. So, that means this we have already accounted for in the previous slide. So, I need to know what is the dimension of this attention matrix. I mean, this is a matrix that will take the attention output and convert. So, it does not compute attention, right. It's just, you can also call it the context matrix, right, maybe the attention context. Okay. So, what is the dimension? 200 cross 100. Right. So, these are the additional parameters that you are using to be able to give an extra context at every step of your decoder. So, you can add the parameters that you had on the previous slide plus the attention specific parameters, and these are the parameters that you need. And this does not take into account the learning of the embeddings for both the languages. If you are also learning embeddings, or if you are also fine tuning your embeddings, then you need to account for going from one hot vectors to the embedding dimension. Okay. So, in the input, so that will be 300 dimension embedding times 40,000 vocabulary. This is if embeddings are to be trained. So, this much you need in the encoder, and similarly for the decoder you need 300 into 50k. And you can see these are much more parameters than what you are working on otherwise, right. So, you need a lot of data to be able to tune these parameters or learn from scratch. So, we do that only when you have sufficient data, otherwise you do not tune these parameters, you go ahead with the normal pre-trained embeddings. Okay. Now, given this problem, now let us go to the encoder decoder model. So, we discussed this model where we have an RNN encoder, RNN decoder, okay, and this is what you do at the inference time. Inference time, you take a sentence, the green which arrived is the input, and you need to generate the output. You are not training anymore, you are just generating the output, right. So, what will happen? You start with the source sentence, its embedding, you compute the hidden vector of the decoder, and you project it to the whole vocabulary space, apply softmax, and you get a probability distribution. So, distribution of vocabulary size, okay, vocabulary of the target language. Now, from this probability distribution, you have to select a token, right. So, what are the ways in which you can generate this token? So, once you have this token, then everything else is very easy. So, you have this token, you feed it at the next time step using its embedding, again compute this, you get a distribution, again choose a token and feed it back, right. So, this is very standard, but what are the ways in which we can choose this token, and these are called the decoding strategy. Okay. So, how do we generate words at each step? Which words do we generate? So, the default method that we use is called greedy decoding, where we always generate the word with the highest probability, and that also some sort of makes sense, right. I mean, you have a distribution at certain step and you say, okay, I will find out the word that has the highest probability and I just output that, right. Typically, we do that in other cases like named entity recognition, classification also, we take the highest probability class. So, maybe we can also generate the highest probability word here, right, and that is called greedy decoding. One question maybe you may be thinking, why it is called greedy, right. That means there is something, there may be some other optimal solution, this may not be the optimal solution, right, but like why would this not be optimal solution, right. So, we are saying argmax of the words among the vocabulary that has the highest probability, that is what we are choosing in greedy decoding. That is the simplest method, right, but can this be non-optimal? So, let us take this example. So, this is a very toy example. So, you are starting from the start token and you have only 3 words, okay, yes, end of sentence, right, that you can generate. So, in the starting you have a probability distribution, you can give 0.4 probability to okay, 0.5 to yes, 0.1 to EOS. So, what would you do with the greedy decoding? I will always choose the word with the highest probability, I will choose yes. Okay. So, I have generated yes. Next, I'll only start, I'll take yes as the next token and generate the next distribution. So this is my next distribution. 0.3 to OK, 0.4 to yes, 0.3 to EOS. Now which of these words I will choose as per the greedy decoding? I'll choose yes again. So again yes. So now I start with a yes, and next time my distribution is only 1 to EOS, others have probability 0. So I have to just choose EOS. So yes, yes, EOS is what I will generate using greedy decoding. Now you can easily see in this toy example, is this the optimal solution? So what is the probability of this generation? 0.5 into 0.4 into 1. 0.5 into 0.4 into 1. So that is 0.2, right? That is the probability, right? 0.2 is the probability. Now, is this any other sequence that has a higher probability? So if I see, okay, with yes, this is the best possibility. What about if I would have taken the second highest probability in the first step? Okay, then I could have again generated OK and then EOS, and this path would have probability. So if I would have generated OK, OK, EOS, that would be 0.4 into 0.7 into 1, that is 0.28. And immediately I can find another path that has a higher probability than my greedy solution. So immediately that means this is not optimal. This is not optimal, right? And it turns out this is also the globally optimal solution. You do OK, OK, yes, right? So we answered both the questions, right? And you can see a limitation of greedy decoding. But then one may say, okay, so then how would I find the optimal solution? So in theory, what would you have to do? You have to say, okay, in the first step, I can generate any of the V possible words. So in the step T1, I can generate any of the V words in the vocabulary. And now you start from each of the V words and try all possible paths. So next step again, you can generate. So there will be V square possible generations, right? Think about the tree with V words in the vocabulary. You have all V tokens. You start from each of these and generate again all V tokens. And you keep on doing that, let's say up to sequence length of T. So what will be the final number of possibilities? Will be V square up to V to the power T. So that means you have to generate all V to the power T possibilities and then choose the one which is the maximum probability among this. And this will be the optimal solution. But immediately you can say this is completely infeasible, right? So even for a small sequence length, because your V is very, very high, we can see 40K, 50K very easily, right? So this becomes completely infeasible. I cannot do so much computation, right? This is like will not run in real time. So what is the trade-off that we typically settle for? So how do we go beyond greedy decoding to get a better solution, but we still avoid exploring the entire search space, right? This is the exhaustive search. You can call it exhaustive search. I search the entire space of possibility of generation. So what is the way in between? And that is where beam search comes very handy. So what is the core idea in beam search? So when you are generating in the decoder, at each step, okay, in greedy I keep track of only the highest probability. So only one in greedy. In the exhaustive search, I have to take care of all V in exhaustive search. So I go in between, I say, okay, I will take care of only K, most probable translations, okay, at every step. That means first step I will choose only K, and now because each of these can again give me K, I will choose from these K square, again I will choose K highest probable sequences, so that it does not it does not increase exponentially. Every time I will limit it to only K most probable completions at this point, K hypothesis. And this K is typically known as the beam size or beam width. In practice, we use 510, sometimes you use also little higher, but you don't go like too much high beam size. Typically, you go around 5, 10, 20, 25. Okay. So how does that work? Okay. So what I will do, so I use my decoder to get a probability distribution, and this method can work for any autoregressive generation where you get a probability distribution and then you want to find out what is the final generation as per beam decoding. So, what you will do, you will have a distribution among all the tokens of your vocabulary. Okay. Now, you would go for, let us say you are using only 2, beam size 2. So, I will take the 2 highest probable words. So, I will take the and arrived. Okay. And this, as if in a parallel universe, I am once trying to feed the next word as the, right, in my decoder. Another time I am trying to feed the word as arrived, right. Then only I can get what is the next distribution. So, I have to feed the word arrived, so that I can compute the next step of decoder. I can compute this probability, and from this probability I have the probability for all the tokens in the vocabulary again, right. So, I have these V possibilities, these V possibilities, right. But then what I will do, I will again boil it down to 2. I will say K. I will two highest probability, the and which, arrived the, arrived which. Okay. Similarly, for starting from the, I will say arrived the green, the which. Okay. So, I have K square possibilities. Okay. So, I have now K square possibilities. Now, I do not go with all K square. I say okay. So, I have now K square partial completions with 2 steps, right. So, I have arrived the, arrived which, the green, the which, 4 possibilities. I want to find out 2 highest probable sequences till now. So, I know the probability of both of these, probability here multiplied by this probability, and we go for typically log probability. So, I can just add log probabilities. So, I can get whichever is the highest probability till now, and I will say okay, I will just go with 2 highest probable sequences. Okay. And then let us say these 2 are the highest, the green and the which. So, I will go ahead with this I have this path, the green, the which, and again I generate 2 distributions, take k from here, k from here, again find only k from here and go forward, right. So, every time I have k partial completions. So, they are partial completions up to step I, and then I use them to generate again partial completion for the step I plus 1. Okay. Okay. So, this is like one complete sort of run for beam search decoding. So, I start for beginning of sentence, and I only keep track of 2 highest probable things. So, this is log probability, and in magnitude lower is better, right. So, this is a lower magnitude. I would have chosen this in decoding, but now I take also the second one. Then I go ahead with both of these. I get another one, probability of the green given x. So, this is minus 0.92 plus minus 0.69, that is minus 1.6, and minus 0.92 plus minus 1.2, right, that is minus 2.1, roughly approximate. And similarly, here I add these 2 probabilities for the and which, right, to get the probability for the entire partial completion, that comes out to be minus 2.3, minus 3.9, right. So, these are my k square hypothesis. I want to choose only 2. I find out which are the 2 of the smallest magnitude, right, because they are all negative. So, I see the green and the which, right, and I am not taking these 2, right. So, let us go ahead with these, and I find again these 2 and these 2. I have the individual probability, I get the probability for the entire sequence by adding it to the previous partial completion. So, minus 3.2, minus 2.1, minus 2.2, minus 4.4. So, I take this and this. Okay. So, which and arrived, right. Fine, I will continue from this, the green which arrived and came, the which arrived end of sentence, the which arrived by. I get therefore log probabilities. I take the 2 largest, that is this and this. I cannot go further from US, I continue from here, and I get another 2. So, this is another EOS. Okay. So, you see, I mean, so you can now get all possible completions, and you may choose the one that has the maximum probability among that, right. So, in this case they both have the same probability, minus 2.7. Right. So, this is how beam search works, and you would with all the beams that you have taken, you would have to see what is the next probability distribution, choose another k from that. Okay. Now, let us try to apply beam search for the previous example we have seen for greedy decoding. So, would it give me the optimal solution? So, let us see, I take beam size 2. So, what will I do in the first step? I will choose both OK and yes, the two words with the highest probability. Next, I will continue from both of these. From OK, I can do either this or this, and from yes, I can do either this or this. So, I have now k square things, probabilities 0.5 into 0.7, 0.28, 0.08, 0.15, 0.2. So, among these, what are the two highest probabilities? This, and this is ignored going forward. So, next I will continue from here. So, this gives me EOS and this gives me EOS, right. So, I have two partial completions, and this is a probability 0.28, this is a probability 0.2. So, I finally select 0.28. So, I get the optimal solution, in this case the globally optimal solution, although you can see it is never guaranteed that even beam search will give you globally optimal, right. It depends on what is the beam size you have taken, and you can always create an example where you have to take the entire vocabulary as a beam size to get the optimal solution, but in practice typically you get a better solution in greedy decoding. Okay. So, yeah, that is how beam search works. Now, little bit on the stopping criteria, because now you do not have a single probability, highest probability sequence. You may get multiple sequences, some may end before than other. So, how do we stop finally beam search? So, in the greedy decoding, usually we decode until the model produces the AND token, right. So, something like a start, he hit me with a pi n. It is very easy, or you can say if I have completed at most at these many words, I will stop. But in beam search decoding, what may happen, different hypotheses may produce this end of sentence token on different time steps, right. We saw that in the previous example also. We were getting EOS at one step before the other sample that we were other path that we were exploring. So, whenever I have got an EOS, that hypothesis is complete. So, what we will do, we will place it aside because we cannot generate next from here, and we continue exploring other hypotheses by beam search, right. So, usually what we do, we will continue this search until either we have reached some time step, say I will not go beyond time step 10, right, whatever I have completed is fine, or we have at least an completed hypothesis. That may be some predefined cutoff. So, any of these I can do to stop my beam search. Now, our list of completed hypotheses. Now, how do we select the one with the highest score? So, you may have multiple hypotheses and they all would have some score. So, which one would you select? So, I am anyway computing the log probability of this entire sequence by summing over all time step, right. I can find the one which has the highest log probability, right. The problem with this is the longer hypothesis would typically have lower scores. Okay. Why does this happen? Because we typically multiply probabilities, each probability value is less than 1. So, as you keep on getting longer and longer sequence, your probability scores will decrease, and when you do log probability, you are adding negative numbers, right. So, as you have more sequence length, you are more likely to have a smaller value, right, or in magnitude a larger negative number. So, what is the solution? So, many times one solution is that because you are just keep on adding log probabilities, you can also normalize it by length. So, that will diminish the length effect. So, you can use divide by the number of time steps to select it. That is one possible trick to avoid this problem. Otherwise, you may just get very short sequence as your output. Okay. And people have seen, for example, in Holtzman paper in 2020, that beam search is typically giving you a very high probability sequence. So, it is seeing what is the probability of the next word that is being chosen, and it is very, very high, right. You can see it is typically very high, but it is less surprising for that region, because they are anyway high probability words, like from the data this word has the highest probability. So, they are very less surprising. On the other hand, if they compare it with how humans have written the text, they are not always like that. They are not always choosing the word with the highest probability. So, human text is not so, I mean, it is actually really surprising, much more surprising than beam search. Okay. So, it is a good method of finding an optimal solution as per your probability space, but it does not always match the way human would write. Okay. That was a very interesting finding. So now how do we get more creative writings, right? I mean, how do we, I mean, we don't want to just stick to highest probability tokens, right? Because they would always be deterministic. So you would always choose the same sequence every time. But you would see, like, there are, if you were exploring recent large language models, every time they may produce slightly different output. So how do you bring out that variation? So that is one thing with the greedy decoding and beam search. So both of these will give you deterministic output. So you are already running them at inference time, and so at inference time means all your model parameters are frozen and there is no randomness anywhere. So what you would do, you would feed the starting sentence, all parameters are fixed, your probability distribution that you will get at the end is also fixed. So whether you use greedy or beam search, your tokens that you will take from there are also fixed. Okay. So you will only get a deterministic output. You cannot be creative there. So there are other decoding algorithms that help in this case, and they involve sampling. So they have some randomness involved. So you would sample a token rather than just selecting the highest probability or k highest probability tokens. So they bring in some degree of randomness. Okay. So how do these work? So let's use this notation to denote that I am choosing x by sampling from a distribution Px. And what is our distribution? It's the vocabulary. On my vocabulary space, I have a probability for each token to be generated. So I have this distribution. I want to choose x by sampling from this. So once I'm sampling, so this can be my decoding algorithm. So each step, I have a distribution. I sample a word, and while this is not end of sentence, I go to next step. I compute the distribution for the next token, right, the whole vocabulary, and then I continue. I sample a word, I compute the next distribution, I sample a word, keep on doing that until I have stopping criteria, that may be EOS. So you sample rather than selecting the highest probability of k highest probability tokens, you sample a word. Now what are the ways you can sample a word? So that's why you do some quality versus diversity trade-off. So various sampling methods, they enable trading of these two important factors. So methods like beam search decoding, they will emphasize in the most probable words. They will produce more coherent and accurate generations, but they are also quite repetitive and boring. So they are good for tasks that are more factual, right? But if you want to do tasks like summarization, creative writing, then they may not be always the best solution. So methods that will give a bit more weight to the middle probability words, that tend to be much more creative and diverse, but they may be less factual, right? So there is always a trade-off between being factual versus being creative, right? So we can do this trade-off through sampling. So we can use different sampling methods through which we can generate more creative completions. Okay. So the simplest one that is used by default is the random sampling with temperature. What is the meaning? So why temperature? So this has some indication from thermodynamics, right? Like because you have a system with high temperature, it's much more flexible and can explore various states, while a system at low temperature is likely to explore a subset of the lower energy, right? So that means at a high energy, you would explore much more vocabulary space. At a lower energy, you will explore a much smaller space of the vocabulary. And this temperature parameter can be between 0 and 1. You don't put it 0, but 0 is open, the interval is open at 0. So you don't put exactly 0, but you can put a small value up to 1. And at 1, you would explore much more vocabulary, and at 0, you will, or close to 0, you will explore very small subset of your vocabulary. Actually, close to 0, that becomes very similar to greedy decoding when you are close to 0. Okay. So how is that actually implemented? So you divide in the softmax parameter, you divide the logits by tau, right? So e to the power xi by tau. That's all you do, right? Nothing else. So this is your temperature implementation. So random sampling. So you simply were doing softmax of u. In with temperature, you would do softmax of u by tau, right? So what is the how? So why does that work, right? So let's take a simple case. So, where you have a probability distribution over the 3 tokens. So, you have the word the, you generated first. Next, you have this distribution, let us say the 3 words with the highest probability. So, in random sampling with temperature 1, so here tau is equal to 1, this is the probability you get after softmax. How does that work? So, you can think of putting them on a number space 0, 0.5, 0.9, 1, and if you get a random number between 0 to 0.5, you generate nice, 0.5 to 0.9 generate dog, 0.9 to 1 generate car. Okay. And let us say you get a number between 0.9 to 1, low probability, but still some probability. So, I generate car. Next, you start from car and you have another distribution, and let us say these are the 3 words drives, age, turns, and next you generate a number between 0 and 0.5, and I generate drives. So, you generate the car drives, right. So, it may be sometimes very incoherent and gibberish. So, what do you do? What happens when you apply temperature, right? So, when you apply temperature, the actual logits are divided by this parameter t, okay, and with the lower t, it will sharpen the probability. Okay. So, what will happen when your t is lower, the word that has a higher probability will even get a even higher probability. We will take an example to see the impact. Okay. So, word that was higher will get even higher. So, rich gets richer when you have a lower t. So, you will say rich gets richer phenomena. So, nice will get even higher probability, and you say the car would get a even lower probability. So, now there is literally no chance of car. There is some chance, but yeah, I mean it would not get selected most likely. So, you select nice, and again you see nice has a new distribution, and this again by a sampling, and you have woman, guy, and house, and let us say you select house. You are anyway sampling, random sampling is still, but your probability distribution is much more sharp in this case. So, you generate the nice house, that is better than the car drives. Okay. So, this works because it tries to sharpen the probability distribution, and the words that were typically low in the probability range would not get a chance. You wanted middle probability words to feature, but you did not want very low probability words to feature, and that is what is avoided by lowering your temperature. You avoid those words. Okay. You can avoid the low probability words altogether through this. There are other variations like top K sampling. So, you say okay, you want to avoid low probability words, so why do you want to even take that into consideration? So, in top K sampling you only take top K tokens as your probability. It looks like beam search, except that you will sample from this. So, you will again apply some sort of random sampling between K tokens. That is not what you were doing with beam search. So, you would only consider top K tokens, but you would do random sampling from that. Okay. So, you choose K, and for each word in the vocabulary you compute the probability and you sort them, find K most probable words. That is what we were doing in beam search, but now you renormalize the score based on these K words. You have a new probability distribution. So, new distribution, and you randomly sample a word within these remaining K words using as per this probability distribution. You again do sampling, that is different from beam search, okay, but only from K words. So, it allows low probability words altogether. Okay. And then there is another variation top P, because top K what it does, it will always take top K words in the probability distribution. So, the shape may differ in different contexts. So, sometimes top K include most of the probability mass already. So, it may also include some low probability words, right. So, and sometimes it may include very small probability mass. So, it may happen all words have roughly uniform probability. So, it will actually include very few words to sample from. So, to avoid that, we say okay, we will select a fixed probability mass always. That is what is the nuclear sampling. So, you select a fixed probability mass. So, say okay, I select top p percentile of the probability mass, say if p is equal to 0.5, I will only select those tokens, those high probability tokens that make the probability mass at least 0.5. Okay. So, it is not top K words, but top words that make the probability words mass to be p, right. So, you want given a distribution, top p vocabulary is the smallest set of words such that the probability for the words in this set adds up to p, at least p, right. So it's easy, you sort them and keep on taking until you achieve P, right? Once you are P or slightly higher than P, you stop. Okay, and you can try this problem to get more idea about how does this work. So I can give you some hint. So your vocabulary of size 5, and this is your logits. So your logits are here. Now you do 3 different type of sampling: random sampling with temperature 0.5, top 2 sampling, and nucleus sampling with probability 0.5. So what would happen if you do random sampling with temperature 0.5? So what I will do now, so when I do soft mix, I will take, so in the first case I will take e to the power 3 by 0.5, e to the power minus 1 by 0.5, e to the power 2 by 0.5, e to the minus 1 by 0.5, e to the power minus 2 by 0.5, and divide by g, that is the summation of all this. And this would be E6, E minus 2, E4, E2, E minus 4. You see what happens, as per temperature, the distance between the probabilities increases, sharpen. So it is much higher than the closest E4, e to the power 2 times higher, right, divided by g. So you compute this, g is simply the summation of this, and you get the distribution, and you can sample from that. Okay. So that's how you will do random sampling with temperature. Now what would I do in top 2 sampling? So in top 2 sampling, actually I have to just compute the probability distribution. So this will be the normal distribution by soft mix: E3, E minus 1, E2, E1, E minus 2, divide by g. I take top 2 words. So which are top 2 words? This and this. I renormalize. So I'll take, okay, E3. So if I need to normalize, it will be simply E3 divided by E3 plus E square, E2 divided by E3 plus E square. And you can also put other words so that your dimensions are matching. So this is your new distribution, and you do random sampling from here, right? What will you do in nucleus sampling with p equal to 0.5? So after you have created the distribution, so again you will start from the same distribution in both top k and top p. But in top p, what you will do, you will keep on adding up till you get 0.5 probability. So in this case, I think as soon as you take the first word, you will get 0.5 plus probability. So you will simply take the first word, something like I think 0.65, and others you will put a 0 probability, renormalize, you get 1, 0, 0, 0, 0. This becomes the distribution. And you do random sampling. In this case, you will only select the first word always. Right? So this is how you do decoding in the typical models, and this is applicable not only for RNNs, also for transformer based decoder model. Okay, and this you can read more in the chapter 10 of our book, so where you have decoding strategy mentioned. So thank you.